Parametric equations. Put your calculator in parametric mode, press mode, down to function. I'll go and do all this. What we're going to do is graph x of t equals sine pi t, y of t equals cosine pi of t, where t is bounded between 0 and 1, inclusive, and here are the directions to do this. So it's going to tell you everything. Now, for parametric equations, this should be a review for everyone, but there's a few that it may not be. If you know an Etch-a-Sketch, if you turn the right knob, that's moving the x values horizontally, and you turn the left knob, that moves the y values. And so here we're going to define x as a separate function in terms of t, and we can think of t as time, and y as a separate function. And so for a specific value of time, we could find the coordinates of the point by plugging in that value of t into the equation for x and y. Let's take a look at doing this problem. I need to cover it up. So now we'll turn this thing on. We have it on. We'll press mode. And what we want to do is move it down. Since we're going to be dealing with trig functions, we want to make sure it's in radians. It is. And then where it says FNC, FUNC, that this will be function, and the next one is parametric. So you move it right arrow and now hit enter, so that's highlighted. Now we can press y equals, and I've already typed in the function, but you just press sine, parenthesis, second pi, and this xt theta n. When you press that, you'll get the t. I need to make sure this is highlighted. So now I have that inputted. I'm going to press window, and it says on the sheet that I want the t minimum to be 0. It is. I want the t maximum to be 1, and I want the t step to be 0.1. X min is -4, y min is 4, scales of negative, or scale of 1 is fine, and then y min -2.5, go down, y max of 2.5, and the y scale is 1. Let's hit graph and see what happens. Now that was pretty fast. What's happening here, when we look at our window, it's starting at 0, and then it goes 0, 0.1, 0.2, 0.3, 0.4, 0.5, all the way up to 1. It plots all those points and connects them. So if we want more points, we can make the t step smaller, and that will have the effect of slowing it down as well. Let's take a look what happens here. So if I make it 0.01, instead of plotting 10 points, it's going to plot 100 points. And so you could see that. Let's sketch that graph. Now the calculator will look more like an ellipse, but it's actually a circle. This value there is 1, this is 1, and this is -1. We have the direction it's going, so we indicate the direction, so we'll put an arrow saying it's going in this way. What are the initial and terminal points? Well, here is our initial. We could see that, and then here is the terminal point. Now, how do you calculate the initial point? The initial point is at our initial time value, which is t equals 0. If we take t equals 0 and plug it into the equation, t equals 0, we will get x equals the sine of 0. And let me state this right now. You must know your unit circle, and you need to know it without hesitation, without thought. We're going to get into trig soon. You need to know all of them, and you need to know the unit circle in a 5-minute period easily, without any hesitation. All standard values, sine, cosine, tangent, from 0 to 360 or 0 to 2 pi, so the degree and radian measures. The sine of 0 is 0. Y equals the cosine of 0, which is 1. So our initial point is, actually I started writing that wrong, is 1 comma Oh, that's the y value, 0, 1. So our initial point is 0, 1. Now we look at our terminal point, and that was at our final time period, or time value. So t equals 1, x equals the sine of pi times 1, which is pi, that is 0. Y equals the cosine of pi, which is negative 1. So our terminal value will be 0, negative 1. Find a Cartesian equation for a curve that contains a parametrized curve. What part of this equation is the parametrized curve? State the restrictions. Note, if the parametric equations are limited, so is a Cartesian. Now, so somehow we need to convert this equation that has t in it, so one that doesn't have any t's. Is there anything that you know that dealing with sine and cosine that we can get rid of the equation with sine and cosine and then get a number out of it? And what should come to mind is the famous Pythagorean identity of sine squared plus cosine squared equals 1. X squared will equal sine squared of pi t. Y squared equals cosine squared of pi t. If we add these two together, we get x squared plus y squared equals sine squared pi t plus cosine squared pi t. And we know sine squared plus cosine squared of an angle theta is 1. So this equation is actually x squared plus y squared equals 1, but we know it's not the whole circle, it's only the half. So what is the domain of the x values? What are the x values here? 0 to 1. And what's the range? What are our y values? Negative 1 to 1. So we're going to state the restriction on there to make that complete. Look at number 2. We're going to do the same thing, except in this one we're going to have a little bit different equation. On your paper it has 4 sine t. Change that 4 to a 2. So we have a little bit of variance on here. We can go ahead and start off and find out what our initial point is. Let's see, we're going to plug in t equals pi, so we'll have x is 4 times the cosine of pi. That would be 4 times negative 1, or negative 4. And y would be 2 times the sine of pi, which would be 0. So we know we're going to start off at negative 4, 0. This is our initial point. Our terminal point, t equals 2 pi, 4 times the cosine of 2 pi, 4 times 1 is 4, y is 4 times the sine of 2 pi, so that would be 0. So we have a point 40 is our terminal point. Now how do you figure out what happens in between? What is going on with that? We could pick a point in between there, say 3 pi over 2. So right now I'm doing this without the calculator. If I do 3 pi over 2, I'll have x is 4 times the cosine of 3 pi over 2. So 4 times 0, 0. Y would be 2 times the sine of 3 pi over 2. The sine of 3 pi over 2 would be negative 1, so this would be negative 2. So that would be 0, negative 2 like this. These are fairly simple function. And we have a graph that looks like there, and we're going in the right direction there. Now let's take a look at what it would be on our calculator. Let me go back to our y equals. Back on y equals. This time I'm going to turn this off. I'll unhighlight it, turn that one on. My window this time I want to go from pi to 2 pi. We could leave the same y value, x and y scale. We can do it as 0.01 just to see it clearly. And because it's 0.01, it's graphing a lot of points there, about 300. And we can see that our graph was correct. Now we need to do the Cartesian equation. How do we go about finding the Cartesian equation? Well, we still have this idea that sine squared plus cosine squared equals 1. So if we look at that this time, we have x squared equals 16 cosine squared t, y squared equals 4 sine squared t. Problem now is if we add those two things together, we're not going to get the exact same coefficient from the cosine squared and sine squared. So what we need to do is make them have the same coefficient. So what could I do to the bottom equation to make it have the same as the top equation? I can multiply it by 4. So I can say, let's say 4y squared equals 16 sine squared. Now if I add these two equations together, I get x squared plus 4y squared equals 16 cosine squared plus sine squared. And I'll go ahead and factor out the 16 to there. So I'm left with 16 times 1. So I get x squared plus 4y squared equals 16, or you could write it as x squared over 16 plus y squared over 4 equals 1 to put it in the form you're more familiar with for ellipses. Now I did it one way there, and I'll quickly show an alternate way you can do it. The problem with that we had over here is we had to multiply by 4 because we didn't have just sine and cosine. We could isolate them in this first part and say that it's x over 4 squared is going to be the cosine squared plus y over 2 squared will be our sine squared, and we'd be left with x squared over 16 plus y squared over 4 equals 1. Either way is fine, it really doesn't matter. Now, do we want the whole thing there? No. What will be our domain restriction? And I'll just put it up here. The domain will be from -4 to 4, and the range will be from 0 to -2. Number 3. Draw this line segment. I'm telling you that it's that. We have 0. Plug it in. X of 0 will be -1, and y of 0 will be 3. So our initial point will be -1, comma 3. And then we have x of 1 will be -1 plus 4 will be 3. And y of 1, 3 minus 5 will be -2. So 1, 2, 3, and then -2. And we're told that it's a segment. Now it doesn't actually tell us to indicate the direction, but we are going here. This is our initial point, and our final point would be 3, -2. Find the slope of this. Well, let's take a look at these numbers. This number here would be what? From -1 to 3, this is 4, and then 3 down, this would be -5. So we have the slope is -5/4. How do the numbers in the slope relate to the numbers in the equation? Take a close look at that. Where do you see -5 and 4 in the original equations? Yeah, right here with the coefficient of t. Is that a coincidence? I think not. When we look at this equation, what's the negative 1, 3 over here? That's our initial point. So when I'm looking at this, I can take a look and say, well, this is the same as my change in y, and this is the same as my change in x. When I'm looking at this original equation here, this negative 1, 3 is our initial point. Now there's other ways to go about it. There's more of a systematic approach that you could just plug and chug that is shown in the book. I think this is easier. Let's take a look at the next part. How would this parametric equation change if it were a line and not a line segment? What makes it the line segment? What gives it the start and stop? That's our values of t. So how would we change that in order to make it so it goes on forever? We would just need to change the values of t. If we want it to go forever, we want it to go from negative infinity to infinity. How would the parametric equation change if it were a ray going towards 3, negative 2? Well, the way we'd have it set up right now, we're starting at 0 at negative 1, 3, and we want to go towards 3, negative 2, and then keep on going from there. So this would say we want to include 0, and then we'll go for our continue going. Now there's multiple ways you can set up equations. This isn't the only one, but given these two set of equations, it would be there. In general, how are we going to set the parametric equations up? Well, if we're going to give a point x1, y1 and x2, y2, comparing it to what we had, you just kind of have this there. We're going to define x of t to be what? We can say x1, because that was our initial x value, plus what does 4 represent? Delta x, so it's delta xt. Y of t will be y1 plus delta yt. Now we could have set the line up in another way. We could have started with the other values. We could have set x equals 3, but if we started at this point, in order to get to the other point, we're going to be going in the left direction, so that delta x would now be negative 4, let me just say plus negative 4 t, and the y would be starting at negative 2, and this time we're going up, so that would be plus 5t. So you can write this the parametric equations in multiple different ways. If this were a line, then the t values would just be negative infinity to infinity. If it were a ray, you would look and see where you want it to start and continue on. If it was a line segment, you would just say 0 to 1, and that would be between these two values.